Greetings. In this one, let's talk about when we have a group homomorphism from some group G to some group H. That there's this property that for any element of a group G, the homomorphism is this function f. We have this property that basically, if we we apply the homomorphism to inverse of an element of the group, it should be equal to when we apply the homomorphism to the element without it being in its inverse, and all of that inversed. And to prove it, we're going to use now the definition of homomorphism says that if we have two elements, A, B, it should be f of A, f of B. Let's say those two elements we take A and A inverse. So f of A and A inverse, homomorphism of A and A inverse, should be equal to f of A times f of A inverse. As you see, we use the multiplication notation for the group operation in this example. So for the identity element, we could also use 1 with this context of using the multiplication notation, but we can also say this a little bit more general perhaps. So we can say this together, A times its inverse, should be equal to the identity element of the group. So I can say f of E, but homomorphism applied to the identity element is, I'm changing it, not changing it. So it's the identity element. This whole thing is the identity element. And on the right side, we can keep this realization. We pick the A and A inverse for a reason, as we will shortly see, or we might already see that. So this thing on the right, we can keep the same. But what we can also do is already rewrite it a bit. So I will apply, we assume it matters because we assume that it's not necessarily a commutative group, and so we'll apply from the left the inverse of this expression. So f of A and the whole thing inverse. Now it might start being evident why this works. So we have f of A, this whole thing inverse, times f of A. So these two things will cancel into identity, and f of A inverse. Well, now we got very far because we basically got to the solution. The E can be sort of crossed out, as it does not change this, and this will together give the identity. So what we got is, yes, indeed, what we were looking for. We directly proved f of A, all that inverse, is equal to f of A inverse, where f is the group homomorphism.